mathematicians. So in last three videos, we were seeing various results regarding diagonalizable matrices. Now, what we do, we collect various uh, diagonalizability related problems from CSR exam and we try to solve them one by one. Okay. Now, if you look at here, I have first we going to do these three problems. If you look at these three problems, they are very similar problems. Okay, let me zoom out little bit. Uh, you see, these three problems. So this is asked in 2017 June, 2014 December, 2019 June. They, I mean, some kind of their repetition. Even the matrix given are different. They require very common idea. Okay, so that is why I have given these the three problems together. Okay, we'll see how we can solve these problems. So basically, all the results we needed to solve problems regarding diagonalizable matrices, we have given it in the part 1, part 2, part 3 of our videos on CSI problems on diagonalizable matrices, that video series. Now we just use the results given there and we will solve these problems. That is the idea. Okay. So let's do the first problem. And so if you look at, so which of the following 3 by 3 matrices are diagonalizable over R? All the matrices given are 3 by 3 matrix. So now we look at the first matrix. So it is in it is an upper triangular form. Therefore, the diagonal entries are its eigenvalues. So eigenvalues are 1, 4, 6. Okay. So basically this matrix has all its eigenvalues are distinct eigenvalues. Okay. Now you if you go to the part 3 video and at the time 13 minutes 15 second, there we have discussed about matrices with distinct eigenvalues. Okay, and we have solved some similar problems also. Please have a look at it there. And so since it has distinct eigenvalue, we get this matrix is diagonalizable. Okay, similarly this matrix also has distinct eigenvalues, this matrix also has distinct eigenvalues. And so we'll come to this problem. So this 1 1 1 1, that matrix has a constant row sum. First row sum also 2, second row sum also 2. Whenever a matrix has a constant row sum, that sum value is always an eigenvalue. Okay, so what is the sum value here? 2 is the sum value, therefore 2 is an eigenvalue. Now trace of this matrix is 2. 1 plus 1 2. So trace is a sum of the eigenvalue. Already we have an one eigenvalue 2. Therefore, the remaining eigenvalue has to be 0. So this matrix has distinct eigenvalues. Okay. Therefore, that matrix is diagonalizable. But we are asked to find the non-diagonalizable matrices. Therefore, this option is false. So for the same reason, this option also false, because these two matrices are diagonalizable, but we want the non-diagonalizable matrices. Okay, good. Now we do the this option also, fourth option also here. So 1 minus 1 2, for we just explicitly calculated the eigenvalues. So you can calculate the eigenvalues. The eigenvalues are 2 and 3. So it has distinct eigenvalues, therefore it is not diagonalizable. So if it is, so it is diagonalizable over R. It has distinct eigenvalues in the field R, therefore it is diagonalizable over R. Therefore this option is false, because we want a non-diagonalizable matrices. Okay, so whenever non-diagonalizability or which of the following statement is false in such problems, always no, just to underline these things so that you won't uh, forget. We are asked to find non-diagonalizable matrices, so you might end up marking the diagonalizable matrices. So even though you've done the problem, you might lose marks. Okay, now regarding this matrices with the constant row sum, we have given a very detailed results regarding matrix with the constant row sum in CSR June 2014 part B question 21. You can in our channel, if you look at this particular problem, there we are talking about this matrices with constant row sum, why that constant sum, that sum value is an eigenvalue. Such things we have discussed very clearly, and this is again an important concept for CSR exam, matrices with constant row sum. For example, this is an all one matrix, right? So all one matrix, all the all one matrices satisfying this condition. Okay, So I mean, one remark is this is a 2 by 2 all one matrix. So it has 2 is an eigenvalue and 0 is an eigenvalue. If it's an n by n all one matrix, then n will be in one eigenvalue, remaining all the eigenvalues will be 0. Okay, this is one remark, better you remember. But again, all those things are discussed in this problem. So you can look at this problem in my channel. Okay. Okay, so let's go to the next option. So this problem we see. So again, we can explicitly calculate the eigenvalues of this matrix. Okay, so I have done the calculation already. The usually the matrices are chosen in the CSI exam such a way that you can easily calculate the characteristic polynomial. Okay, so what is a characteristic polynomial? You have to calculate determinant of lambda I minus a. So or determinant of xi minus a. So basically, you take a diagonal matrix with all the diagonal entries are x, and then you subtract a from that matrix, so you get this matrix. So the determinant of this matrix will be the characteristic polynomial. If you calculate the characteristic polynomial, you get x cube minus x square plus x minus 1. So if you look at the matrix, immediately you can say 1 is a root of this polynomial because sum of the coefficient is 0. 1 minus 1, 1 minus 1, if you sum them 0, if the sum of the coefficient is 0, then 1 is a root. So therefore, we know that x minus 1 is a factor. So we have to find the remaining degree 2 factor because it is a degree 3 polynomial. So how do you find the degree 2 polynomial? Again, we can use things learned from the school. So you put a 1 here because 1 is already a root. Then you put the coefficients here, 1 minus 1, 1 minus 1. So we always put a 0 here. Then 1 plus 0, 1, 1 into 1, 1. Minus 1 plus 1, 0. 0 into 1, 0. 1 plus 0, 1. 1 into 1, 1. Minus 1 plus 1, 0. You should always get 0 here because 1 is a root. Okay. So then this three values corresponds to x square plus 0x plus 1. Okay. So that is basically x square plus 1. Now the root of the polynomial x square plus 1 is I and minus I. Okay. So what we conclude is the eigenvalues of these matrices are 1 I minus I. Okay. In our first video, part 1 video, please check part 1 video. There we have proved that to diagonalize a matrix over the field F, all its eigenvalues should be in the eigenvalue F itself. Okay. In particular, to diagonalize a matrix over R, its eigenvalue should be R. But this matrix has complex eigenvalues. Okay. 1 I minus I. Therefore, this matrix is not diagonalizable over R. Okay. One easy way to see is if you have seen rotation matrices, then this is an rotation matrix. Okay. Rotation matrices are, I mean, rotation matrices are diagonal. Actually, it is rotation by 90-degree. Uh, so if you have to observe that E3 is going to E3. So for third column is E3. That means that so if that I mean so E3 goes to E3. Enough to you look at only uh, okay. So first column is the image of E1. Second column is the image of E2. Third column of the image of E3. E1, E2, E3 are standard basis. Now this is the image of E3. Image of E3 is again E3. Okay, so if image of E3 is again E3, enough you just look at this 2 by 2 matrix. Okay, so basically what it does, E1 goes to minus E2, E2 goes to E1. I'm just saying this 2 by 2 block. Okay, in R2, so this is R2 to R2 to R2 matrix. This matrix is R2 to R2, it is rotation by 90-degree because 0 comma 1 goes to 0 comma minus 1. 1 comma 0 goes to 0 comma 1 goes to 1 comma 0. So it is a rotation matrix. Okay, that part I am going to delete it. Leave it. So we come to, so there is one idea. You don't need to do all this calculation to there is one very simple idea to conclude that this matrix is not diagonalizable. So this is a rotation matrix. So if you can see that it is a rotation matrix, then you can see that it is a rotation by uh, 90 degree in each of the plane parallel to xy plane. Therefore, a rotation matrix is diagonalizable if and only if it is rotation by 0 or rotation by pi, 180 degree. But it's a rotation by 90, therefore not diagonalizable. Yeah, so I have made a video on rotation matrices. So please check that video if you want to know further about rotation matrices. Okay. Anyway, you can directly calculate eigenvalue also and conclude this matrix is diagonalizable. It is not. It is fine. Okay. Now this is a real symmetric matrix. Okay. So real symmetric matrices are diagonalizable. Okay. So if you take the transpose of this matrix, you will get back the same matrix. And so a real symmetric matrices are diagonalizable over R. So we have discussed about real symmetric matrices in our part 1 video at that time 15 minutes 42 seconds. So please check why real symmetric matrices are diagonalizable. Now we come to the fourth option. So again fourth option, this matrix is in the upper triangular form. Therefore diagonal entries are 0 0 0. Okay. But more is true. This is a strictly upper triangular matrix. Strictly upper triangular means diagonal entries also 0 0 0. Okay. So for such matrices, the eigenvalues are 0 0 0. Therefore, the characteristic polynomial is x cube. By Cayley-Hamilton theorem, this matrix should satisfy its characteristic polynomial. So we get a cube equal to 0. So a cube equal to 0 means basically that matrix is a nilpotent matrix. And if you see in at part 1 at 7 minute 23 second, we have proved a very general result. If a matrix has all the eigenvalues are equal, then such matrices are not diagonalizable. That we have proved here. Okay, please check part 1 video at 7 minutes 23 second. By that result, this matrix has all the eigenvalues are equal. So we conclude that any nilpotent matrix is not diagonalizable over R. You see, for the same reason, it is not diagonalizable over C also, nilpotent matrices. Okay, so this option is false. Okay, good. So let's. I gave this problem. We have already solved this problem at part 3 at this time as application of arithmetic multiplicity and geometric multiplicity. So please check at 13 minutes 15 second on part 3. But here I gave this problem nevertheless here because we want to compare how similar problems are asked in the CSR exam repeatedly. For that reason only I have included this problem here. Okay, so please see what. So please look at this particular time on part 3 to see what is arithmetic mean, what is geometric mean, and a matrix is diagonalizable if and only if arithmetic mean is arithmetic multiplicity, geometric multiplicity, not mean, geometric mean. We have to say arithmetic multiplicity, geometric multiplicity. A matrix is diagonalizable if and only if its arithmetic multiplicity equal to geometric multiplicity for all the eigenvalues. Okay. So in this video, we have proved that one of this matrix satisfies arithmetic multiplicity equal to geometric multiplicity, and the other matrix doesn't. So whichever matrix is satisfies, it is diagonalizable. The other is not. So you can check the video at this time to conclude which one of them is diagonalizable, which one of them is not. Again, using this, if you look at these two matrices, if you can compare these two matrices with these two matrices. Okay, so these two matrices also have two distinct eigenvalues with one eigenvalue repeated twice. Okay, here also these two matrices have two distinct eigenvalues with one eigenvalue repeated. Sorry, here these two values repeated. Okay, so basically you have to find the arithmetic mean and the geometric mean of the eigenvalue 2 and 2 and 3. Then if the arithmetic multiplicity, sorry, whenever I am saying arithmetic mean, geometric mean, please take it as arithmetic multiplicity and geometric multiplicity. Okay, so 2 is an eigenvalue, 3 is an eigenvalue, distinct eigenvalue. So you look at the arithmetic multiplicity of 2 and geometric multiplicity of 2. if they are, check whether they are equal. And for anyway, 3 has arithmetic multiplicity 1. Whenever a root has arithmetic multiplicity 1, its geometric multiplicity also 1. You don't need to check. So only for the eigenvalue 2, you check its geometric multiplicity. How to check geometric multiplicity? You can see how we have calculated here at this place. Okay. So using the same idea, you can solve these two problems and you can find which of them is diagonalizable, which of them are not. Okay. So our basic idea is whatever results we need to regarding diagonalizable matrices, it is all given in part 1, part 2, part 3 videos. Okay. So without that videos, now I have to uh, keep saying each and everything repeatedly. Okay. But that is again time consuming, it is not good also. So if you watch the part 1, part 2, part 3 very clearly, then you already know all the results related to diagonalizable matrices. You can do all these problems very easily. Okay. So in next 2 3 videos also we completely solve all the diagonalizability related problems asked in CSAR exam. Again we keep repeating to keep repeatedly referring to part 1 video, part 2 video, part 3 video at particular time, like that. So please go through the 3 videos on diagonalizability once clearly. Also there are many problems solved in part 1, part 2, part 3 videos. So it is really good to watch those videos. Okay. So I hope you understand uh, how to apply our results in solving these problems. If you have any doubts, please let me know in the comments, and please do this calculation and let me know which one of them is diagonalizable, which one of them is not, and please tell in the comments. I'll be very happy to know. Okay, guys, take care. I'll see you on some different problem on diagonalizability tomorrow. Thank you.